Welcome to Lesson 7.7, Properties of Parallelograms. So, in this section, obviously, we are moving on from triangles, but you will see that these parallelograms can be broken down into series of triangles or overlapping triangles. But today we are just going to start with looking at some of the basics and properties of parallelograms. So, all four of our main properties are summarized into the properties of a parallelogram theorem. And that theorem simply states in any parallelogram, part A, first we know, opposite sides are congruent. So if we look at the parallelogram drawn over here, we know that side AB is congruent to side CD, and we also know side BC is congruent to its opposite side of AD. Then part B of the theorem says in any parallelogram, opposite angles are congruent. So in that case, we know angle B is congruent to angle D, and angle A is congruent to angle C. Then we know consecutive angles are supplementary. So a reminder, supplementary means they add to equal 180 degrees. So any consecutive angles would be ones right next to each other. So that would be angles A and B, A and D, B and C, and C and D. So again, consecutive angles are supplementary, meaning they add to 180 degrees. And then the fourth part of our theorem says in any parallelogram, the diagonals intersect at their midpoints. So in our drawing over here, we have the diagonal segment AC and the diagonal segment BD. So if they are being intersected at their midpoints, what we know is if that midpoint is E, segment AE is congruent to EC, and segment BE is congruent to ED. So all those four parts make up the properties of parallelogram theorem. So if you ever were needing to use any of those properties in a proof, what you would write for your justification would be the properties of parallelogram theorem. So example 1 is a 2-column proof based on the given that we are given parallelogram ABCD. They would like to prove segment AB is congruent to CD and AD is congruent to CB. So what they are basically doing here is that we are proving that part of our properties of parallelogram theorem, opposite sides are congruent. So the idea of this proof, we wish to prove something about parallelograms, but all of our previous work was based on triangles. So in order to build some of these properties of parallelograms, which you'll see with many shapes in the future, a lot of the properties start based around proofs and properties dealing with triangles. So in this case, they drew in diagonal AC so that they could look at triangles ACD and CAB along with the numbered angles 1, 2, 3, and 4 in the drawing. So the first thing is the given ABCD is a parallelogram. Then side AD is parallel to BC. That comes from the definition of a parallelogram, which states opposite sides are congruent. Or, sorry, should not say congruent right there. Should say opposite sides are parallel. My mistake. So, definition of a parallel or of a parallelogram states opposite sides are parallel. Then the parallel lines theorem, which includes alternate interior angles being congruent, allows them to state angles 2 and 4, right here and here in our diagram, are congruent. Then we know segment AB is congruent to CD from the definition of a parallelogram, which again, opposite sides are parallel. Then angle 1 and angle 3 are also alternate interior angles, so we can say they are congruent from the parallel lines theorem. If you would write in a proof alternate interior angles are congruent, I'm also fine with that because that is part of the theorem. Then in part 6, they said segment AC, our diagonal, is congruent to itself, which is the reflexive property of congruence. Then they were able to use angle side angle congruence theorem to state triangle ACD is congruent to CAB. And then because of the corresponding parts and congruent figures theorem, we can state that side AB is congruent to CD and AD is congruent to CB. So using the properties and proof ideas and theorems related to triangles and parallel lines, we were able to prove some of the properties of a parallelogram. Example 2 is more based simply on the properties. So what we know is in parallelogram MATH at the right, segment FT is 5, MA is 8, and the measure of angle MHT is 80. Find the following measurements. So first they want us to find segment FM. FM, right here, is half of this diagonal, MT. So if FT is 5, FM is the same, which is also 5. Segment HT, the bottom here, is opposite segment MA. So opposite sides are congruent, meaning both are 8. Then angle MAT, the one right here in this corner, A is the vertex, is congruent to its opposite angle of MHT, so both are 80 degrees. And then to figure out angle M or angle HMA, so angle M up here in the corner, vertex of M, that would be supplementary to angle H or angle A. Either way, it is 180 minus 80 degrees, giving us angle HMA is 100 degrees. Then we have two other theorems related to parallelograms and parallel lines. There's the theorem based on the distance between parallel lines, which simply states the distance between two parallel lines is a constant, or is constant, meaning whatever distance between the parallel lines is measured, it would always be a constant number. So segment AB would be the same as CD, the same as EF. It's a constant number, not going to change. Then the other theorem that we're looking at is the parallelogram symmetry theorem. That simply states every parallelogram has two-fold rotation symmetry about the intersection of its diagonals. So remember, symmetry about means symmetry being spun around a point. So that would be like saying we pin down this point right here and we spin the parallelogram around it. So it has two-fold rotation symmetry because it would be the same orientation in this setup, or if we rotate it 180 degrees, it would also look exactly like this. So example 3 says use the figure at the right. NOLA is a parallelogram with P, the midpoint of diagonal OA. So part A says under a rotation of 180 degrees with the center point P, what is the image of NOLA? So remember that a pre-image is our original shape. The image is the final shape or final figure after the rotation. So 100-degree rotation would mean we go counterclockwise because it's positive. So think about spinning this parallelogram 180 degrees around point P. So then where originally point N is, that would now be vertex L, because 90 degrees would put L up here, 180 degrees would put it right here. So then in that case, the N would become L, the O would become A, because that again, A with 180 degrees, 90 would move over here, 180 would put it right here. So our new image, the new name would be LANO. In part B, if the measure of angle ANO is 3x plus 80, and the measure of angle OLA is 6x plus 5x, find the measure of angle NAL. So first we need to look at angle ANO, so A to N to O, this angle up here, and angle OLA, this angle down here, which is opposite that. So I know these two angles are equal. So I can take these two expressions and set them equal to solve for x. So when I do that, I get x equals 6. Then I want to plug that back in to either of the expressions to get that angle measure. So I plug that back into angle NAO. 3 times 6 is 18, plus 80 would give me 98 degrees. So I know angle N up here and angle L down here opposite it are both 98 degrees. But that is not what the question was asking. It was asking us to give measure of angle NAL. So to get NAL, the missing angle down here, we know that is supplementary to its consecutive angle of 98 degrees. So we do 180 minus angle ANO, 98 degrees, giving us the measure of angle NAL at 82 degrees.